on today's colloquium. It's my pleasure to introduce Will Coulton, who's a Cavalry Fellow at Cambridge University. That's the latest stop in his truly transatlantic career by now. Will started out as an undergrad in Oxford, moved to Princeton for his PhD, while with David Spergel. After that, moved to Cambridge, and then through Japan, due to COVID related policies of the US, moved to CCA as a CCA fellow, and now he's back in Cambridge as a senior Cavalry Fellow. Will is a really broad cosmologist, working both in large-scale structure, higher order statistics, and in a cosmic microwave background, all the way from pixel level or detector level data to cosmological interpretation. And as an example for that, if you came to his physics colloquium last spring, don't worry, you'll hear something completely different today. Last time we heard about primordial trinity. Today we hear primarily about CMB secondary anisotropies. So please take away.
Great, thank you very much for the introduction and the opportunity to speak. So today I'm going to be talking about what we can learn about galaxy groups and clusters with precision measurements of CMB secondary anisotropies. And I'm primarily going to be talking about this in the context of the Atacama Cosmology Telescope shown here, which is a telescope, as you would expect, located in the Atacama, which is a great place to observe the CMB, being assured that the sky looks like that, at least in millimeter wavelength. And so the work I'm going to present today is there's contributions from many people across two collaborations, the Atacama Cosmology Telescope and the Simons Observatory collaboration. I'll highlight a few of these going through, but I'd like to highlight the work of Zach and Adri, who have contributed enormously to some of our behind-the-scenes work and the results that I'll present today. So as I'm sure many of you are aware, in the last few decades, our ability to make realistic simulations of the universe has dramatically improved, such that the state-of-the-art are able to simulate large swathes of the universe that end up looking a lot like realistic galaxies that we see in telescopes. Here is an example showing a simulation showing the gas density from the illustrious TNG collaboration. This produces galaxies that match many of the observed properties we see in telescopes. However, despite these successes, there is still a lot of theoretical uncertainty. You can see this in this video where the blue regions show the gas density and the red regions show gas temperature. This compares the same universe with the same initial conditions through 4 state-of-the-art cosmological simulations, the TNG model, the SIMBA, the Magneticum, and the Astrid simulation suite. And what I think jumps out by eye is that these simulations are not just quantitatively different in terms of the gas temperature, for example, they're qualitatively very, very different. As you might imagine, this kind of qualitative differences has huge implications for a diverse range of observables, ranging from things like the fates of galaxies, which depends on the properties of the surrounding gas, the so-called missing baryon problem, where we do a census of where we think baryons are, and a large fraction of them seem not to be accounted for, and potentially even in cosmological tensions, where comparisons of the clumpiness of the universe versus the amount of matter in it compared in the early universe from Planck with various late-time sources are potentially showing a tension in our cosmological model. However, to understand this, we really need to know where the matter is, and that's hard if we have significant theoretical uncertainties like we saw in the previous slide. So what is driving these discrepancies? At the scales that we're going to be thinking about, which is the most massive objects in the universe, this is being driven by active-galactic nuclei feedback, particularly in the form of strong radio jets dumping mechanical energy into massive objects and powerful quasar winds for displacing and heating gas. The big challenge here is that there's a humongous dynamical range involved. The scales relevant for modeling AGN feedback are the scales of the accretion disk and the physics around the black hole, and we're interested in the impacts of these on cosmological scales with the many, many orders of magnitude large. This means it's unfeasible with our current and foreseeable methods to simulate all of this ab initio. This results in approximations in how these are included and how their effects are included in cosmological simulations. That's one of the limiting factors in the predictions I showed before. So why am I talking about galaxy groups and clusters in this context? Well, actually, we've known for a very, very long time, thanks to X-ray observations, that AGN feedback plays a very important role in objects. These objects are filled with very hot gas, sort of tens of millions of Kelvin. This radiates in the X-rays, shown here in this lovely Chandra composite image. What's interesting is in the central region of many types of clusters like this, the rate of cooling is so rapid that we would expect these to have cooled much below the temperatures we observe them to be. This means that there must be a tremendous source of energy continually sort of heating the central regions of these clusters so that they don't cool as you might expect from the amount of radiation going. Galaxy clusters are a very interesting regime for studying feedback. One, because it's sort of at the extreme end where the most energy injection of feedback is happening, but also because these objects are so massive and have such deep potential wells, the effects of feedback are mostly to redistribute gas rather than driving it completely out of the clusters. This means we have a hope by studying the properties of these clusters to learn things about the processes that are going on. An example here is from some lovely eROSITA data that the collaboration made public actually last week, which I think is very exciting. And here it compares measurements of the gas entropy in the outskirts of the clusters to their measured temperatures. And we compare it, and they compare it to simulations where they don't have AGN feedback in, and you can see with massively discrepant results. And they compare it with one example, in this case from the OWLS simulations, which shows better agreement, but still quite large discrepancies. And so the idea of what I'm going to be talking about mostly today is how we can use CMB observations to advance our knowledge of the gas properties in objects like these, and use that in turn in the future to close the loop and inform us about what is the physical processes going on and the microphysics involved there. So many of you are probably familiar with the CMB as a cosmological observable that now for over 50 years has shaped cosmology as a field. The cosmic microwave background is this bath of photons that surrounds us and permeates the universe. And it was created early on in the history of the universe when the universe transitioned from being a hot and opaque plasma, undergoing recombination when it was about 400,000 years old. And then since then, standard story is these photons have propagated through the universe. This means that observations of the cosmic microwave background have been used to tell us about the macroscopic properties of the universe, and also have been very informative about the physics going on in the early universe, potentially constraining the physics of inflation. But what I'm going to talk about today is hopefully showing that these kinds of observations can actually give us information about the kinds of processes that have happened basically all the way in between after, say, the Dark Ages. And one of the ways that you can see this is actually visually in this lovely video that my collaborator Sigurd Ness put together. This is a telescope scanning the sky, and in the left-hand side, in this side over here, we see the sky as it was imaged by the Planck satellite, which is the state of the art 10 years ago. And on this side, we show a composite image of data from Planck with a high-resolution, lower noise instrument, the Atacama Cosmology Telescope. What you can probably see is the fuzziness on these CMB anisotropies decreases, which shows that we're measuring the primary CMB anisotropies much, much better. So the thing that maybe jumps out even more is the fact that there are all of these red sources that jump out. If you're careful, you might see a dark blue one. And these are other sky signals that as we increase our sensitivity and precision, we gain increasing sensitivity to. And these contain a wealth of information about late-time properties. So there are a range of different signals from the extragalactic universe that contribute to our observations here. The bright red objects you saw are probably bright radio galaxies or potentially dusty star-forming galaxies. These are signals that generate emission that we observe in the millimeter wavelengths where we observe the CMB. Today, I'm primarily going to focus on a range of signals which are known as CMB secondary anisotropies. These describe distortions to CMB photons that happen to a small number of them as they propagate from the surface of our scattering here to us as we observe them. One of the ones that you're probably most familiar with is gravitational lensing, which describes how the trajectories of CMB photons is deflected by intervening matter. But there's actually a whole range of these. Each one includes something interesting and different about the physics of the late-time universe. Another famous one is the integrated Sachs-Wolf effect, which occurs as potentials evolve with time. And one that I'll talk a lot about today is the thermal Sunyaev-Sedovich effect. And I'll discuss the details of this in the couple of slides. Of course, there are also galactic signals that contribute to our observations in the millimeter wavelength, as demonstrated by these amazing images from Planck. I'm not really going to talk too much about galactic science in this talk today, but there's a lot of very interesting work going on in ACT and SO. And if you're interested in that, perhaps we can chat about it after. Instead, what I'd like to take from this is that these signals visibly show a very different frequency evolution compared to the CMB anisotropies, which you can see in the top here. See, the synchrotron is dominant at low frequencies and then reduces, and dust becomes very dominant at high frequencies. Additionally, that you can see that the spatial properties, the CMB, so we think the CMB is the black body distribution with very small Gaussian perturbations on top of them here. You can see the statistical properties of the galaxy are very different. They're very non-Gaussian, they're very anisotropic, localized mostly in galactic plane, as you would expect. And the idea I want to take away here is that we can think about using these different components.
Can we make it louder, please?
Perhaps raise your mic.
Is that better?
I'm watching remotely, I can't hear.
Is this better?
Not much.
Does someone know how to use the controls?
I don't know how those work.
Perhaps I can continue perhaps holding a bit like this while someone comes and tries to work with the controls. Is this better?
Slightly.
Sorry. So underpinning the rest of my talk is going to be the idea of component separation, which uses these different the different frequency dependence of the different sky signals. In this case, we're going to be thinking about the extragalactic ones, and also their different statistical and spatial properties, and combining these to isolate from the plethora of signals that we have in our data sets one component of interest. An example here is shown how this works for the primary CMB. So I mentioned this at the very beginning. The data that I'm going to be primarily talking about comes from the Atacama Cosmology Telescope, or ACT, which is located in Cerro Toco in the Chilean desert. This is a great place for CMB observations, as it's very high and the atmosphere is very dry. So as a result, there are actually a range of CMB experiments that you may have heard of before, the polar bear and class experiments, some future experiments such as CCAT Prime, and the Simons Observatory is being built here. And then actually just a mountain over, there is ALMA, which I'm sure you've all heard of and maybe even used. So the Atacama Cosmology Telescope was a telescope that operated for about 15 years. In 2022, it actually finished its operations. And here's a kind of a quite sad photo for us of the telescope being dragged back down the hill. It was a 6-meter off-axis Gregorian telescope that observed the sky at 5 different frequencies: 30 gigahertz, 40 gigahertz, 90 gigahertz, 150 gigahertz, and 220. I'm going to be primarily talking about results from these 3 frequencies, as we're still working on reducing and fully understanding these data from lower frequencies. The site in Chile is great for another reason, not just that it's high and dry. It is able to observe a very large percentage of the sky. We're actually, in principle, able to observe almost 50% of the sky. In the past, our observations have covered more like 30% of the sky in this sort of regime shown here. And this is very useful, as it means it overlaps with lots of other surveys you've heard of and can enable very powerful cross-correlations between CMB data and, for example, optical surveys or radio surveys, actually. The other experiment that I will talk very shortly about is the Simons Observatory. This is a new experiment that's actually being built on the exact same place where the Atacama Cosmology Telescope was being built. This photo is now quite old, and the construction of this is well on its way, and we expect to have first light hopefully later this year. This facility actually is composed of multiple telescopes, a large 6-meter telescope with slightly extended frequency coverage compared to ACT, and at the moment 3, but soon to be 6 small aperture telescopes that are designed to search for the signals of primordial gravitational waves. So with this, I'm going to spend most of the rest of the talk discussing different components on the sky and how we're using them to learn different aspects of late-time physics. So the first one is the thermal Sunyaev-Zel'dovich effect. This effect occurs as photons propagate through the universe and they encounter hot electrons, and these photons inverse Compton scatter off these hot electrons, gaining some energy. The result of this is that in the directions of lines of sight where we encounter hot gas, we get a shift of the spectrum of the CMB photons from this black body with 2.7 Kelvin to higher frequencies. They all gain energy. It's very common in the CMB community to work in so-called linearized differential thermodynamic units, or CMB units, which describes the measured intensity relative to this black body of the CMB. In these sorts of units, what this signal looks like is at low frequencies, a decrement, as there are fewer photons with low energies, and at high frequencies, an excess. This signal is very interesting for many objects. The frequency dependence of it is independent of the properties of the gas, and it can be written as the anisotropies that we see depend on this frequency-dependent function and a parameter we call the Compton Y effect, which measures the integrated line of sight pressure between us and the surface of last scattering. As you might have guessed from what I said earlier, one of the regions that produces the largest source of thermo-Sinazodovic anisotropies is galaxy groups and clusters, which are filled with hot ionized plasmas. Here is showing an extract from a simulation of the Compton Y effect, and what you can pick out by eye is many, many bright clusters. This effect is actually very interesting for studying the properties of these objects, as the pressure in them, as you might expect, depends a lot on their history. In particular, here is an example comparing a map that you would get without AGN feedback to a map that contains AGN feedback. And by eye, you can spot significant differences between the two, which gives us a hint this might be a useful probe for understanding the physics of these objects. So in the recent years, what we have done is use the frequency dependence of this effect to extract a map of the Compton Y anisotropies. And what I'm showing here is that map. This map is going to become publicly available, so people in the community can use it along with ancillary products in the coming weeks. What you can see by eye is many of these bright yellow dots. Each one of these is a galaxy cluster. Some of you might recognize clusters you know, such as Virgo cluster, and the Bullet cluster is just in our footprint as well. To measure this, actually, we really benefit from the high resolution, low noise measurements that we're making from the ground with these large 6-meter telescopes, for example. And you can see this by another video comparing what the Planck Compton Y map looks like compared to the ACT and Planck Compton Y map. What you can see is many, many white objects here jump out as we transition across into ACT data. And that's the power of having this high resolution data allows us to isolate these sort of small arc-minute signatures of galaxy groups and clusters. I think it's quite incredible that you can count many of these by eye. So what can we do with things like this? Well, one thing we can do, of course, is cluster cosmology, measuring the differential counts of clusters as a function of mass and redshift. Has been a historically very powerful way of learning about our cosmological model. We've now detected over 4,000 clusters in our publicly released catalog, including over 200 of them at redshift 1. I'm going to be talking a little bit more about sort of the astrophysics of this, and one example of what we can do with these is studying individual objects and using them as a laboratory. Here is a system that we call the bridge system between two Abel clusters, and this pair of systems has a filament connecting between them that we're actually able to now measure on its own. And this, in combination with X-ray data, for example, is informing us about the physics of the gas within this, constraining its properties such as its temperature and density. We now have many such types of pairs like this in our data sets. The other thing we can do is cross-correlate our Compton Y map with other observables, as I suggested earlier. Here is a result showing, led by Shivam, showing the cross-correlation between the Compton Y map and a distribution of matter in the universe as measured by the Dark Energy Survey. Here we're comparing the equivalent measurements between Planck, the old ACT data, and the latest ACT data, where you can see the error bars are shrinking. This difference you see here is not systematic. This is the difference in resolution of the Planck instrument versus ACT. This measurement has been very exciting, as because interpreting this measurement has shown that the gas, the amount of Compton Y, or amount of pressure in lower mass galaxy clusters, is lower than we'd expect from self-similar scaling relations, which in this plot would be a more flat line. And this deviation is expected to arise due to AGN feedback. And so by performing more and more precise characterizations of that, we can turn this around to learn about the processes driving that. One thing I'd like to very briefly touch on is, in order to interpret measurements like this, we need to build physical models, and this can either be done using analytic tools like we just discussed, or using simulation-based methods. Here I'm showing some work by a graduate student I worked with, Leander, and here the idea was working to make fast synthetic maps of the Compton Y effect. Normally this would require running expensive hydrodynamic sims, but he was working on a way to convert dark matter particle simulations only to produce accurate maps of the Compton Y effect. In this method, I think it was quite an interesting approach where he used neural networks, but he broke it down into a series of different operations that each one of them we tried to associate physical meaning with. And in it, we tried to embody the physical symmetries of the problem, such as rotational and translational invariance. And so, for example, he had a module that contributed the stochastic fluctuations around the mean part of the signal. In principle, this means we can turn these things on and off to work out how important, for example, accounting for ellipticity of the halos is when performing this painting operation. That I'd like to move to a very related component, which is the relativistic Sunyaev-Sundovich effect. So I said earlier that the anisotropies caused by the thermal Sunyaev-Sundovich effect don't depend on the properties of the object, but this is actually only an approximation, which is valid for most of the gas in the universe. The approximation is that the temperature of the electrons are non-relativistic, so the temperature is much, much less than the electron mass. However, we know that for the most massive objects, this isn't true, and this kind of formulation breaks down, and we need to account for a more thorough treatment where the frequency dependence actually does depend on the temperature. You can see here how this frequency dependence changes as the gas temperature varies from a very low temperature, which is effectively non-relativistic, to higher and higher temperatures. One of the things we've been exploring, and unfortunately the results I can only show at the moment are simulations, you'll have to stay tuned for the database results, is using this effect and turning it around to see, can we use this dependence on the temperature of the objects to measure the Y-weighted temperature of these objects. And so here's an example of how this works on simulations. In this case, we know what the true input cluster temperature is, and we've measured in simulations the temperature of a stack of clusters in an analysis similar to what you would expect from ACT data. This is interesting, as we can use this to potentially constrain the temperature evolution of these objects as a function of mass or redshift. For this first sample we've been considering, you're not really able to get very interesting constraints on it. This is more of a demonstration of a proof of principle, because for something like the Simons Observatory or CMB stage 4, which will dramatically improve upon the ACT result, our signal to noise on this measurement is going to dramatically increase. And not only that, the number of clusters we're going to have is going to range increase from 4,000 in ACT to maybe 25,000 with SO to over 100,000 with CMB stage 4. With these kinds of samples, we're really going to be able to understand the evolution of the temperature, the Y-weighted temperature of these objects. The next component I'd like to talk about is gravitational lensing of the CMB. This effect is perhaps something that you've heard about. It's been a very powerful probe in the CMB community for maybe the last decade. The idea here is that as the CMB photons propagate through the universe, their paths are deflected by intervening matter. And this actually distorts the statistics of the CMB. It doesn't change their black body spectrum, but it makes them slightly non-Gaussian. And the idea here is that we can use the specific form of non-Gaussian coupling to invert this to make maps of the integrated mass distribution between the surface of Lahr scattering and us here. An example of this is shown here in some work led by my collaborator Frank. This is a map of the integrated matter in the sky observable by the Atacama Cosmology Telescope. This really improves on the small scales compared to the previous best. And this is publicly available for anyone to download and use for a range of interesting projects. One of the things I think is really cool about this is that you can sort of do correlation by eye. Here we've taken a small zoom in of this map, showing here in light and dark regions the fluctuations of over and under densities of mass. And we can compare it to the distribution of star-forming galaxies at high redshift, where we get most of our sensitivity here. And this is shown in the different colored contours here. What I think is really amazing is by eye you can see that these trace each other, which shows the high fidelity reconstruction of the mass map that we've been able to do now. So what kinds of science can we do with these types of measurements? Well, one thing we can do is the common cosmological approach, which is to measure the power spectrum and make inferences about cosmological parameters. This potentially gives us a way of weighing in on some of the cosmological tensions I briefly mentioned earlier. In the context of this talk, what we can use it to do is actually to measure the mass of galaxy clusters. Here I'm showing a result produced by Matt, where he used CMB lensing to measure a sample of the Mad Cows clusters, which are a set of galaxy clusters of about redshift 1. We're also able to do this on samples of much lower mass clusters, which is some ongoing work that hopefully will be appearing on the archive soon. One thing I'd like to take a slightly more technical detour for just a few slides to comment on upcoming observations. So the current best approach we've used throughout the community is an approach that for our current observations is close to optimal. And this is an approach that you might have heard of known as a quadratic estimator, which gives you a point estimate of the lensing potential. Comparing it by eye, this is actually quite a noisy reconstruction. And for the next generation of experiments, this kind of approach is actually very suboptimal. In this work, led by a student, Thomas Floss, who came to work with me at the CCA on this project, we've developed an alternative method that's able to make a much higher fidelity reconstruction. And actually, you can show that this is close to as well as you could possibly do. And this is an example for an upcoming experiment, but as measurements continue to get better and better, the discrepancy between the standard approach and approaches like this just increases and increases. And so this method is actually taking advantage of some recent developments in machine learning. I'm sure every one of you here has now seen images and probably played with generative image models such as DALL-E. The idea here is thinking about it going this way: is we take an image and we continually add white noise, making a random walk through the process until we end up with a map that just contains white noise. The idea here is that this reverse process can also be characterized by a stochastic differential equation with just one additional component that we parameterize with a neural network. The idea is we learn to remove the noise at each step here to manage to go from a white noise realization to, in this case, the image of a dog. The idea we've been considering here goes one step further and is kind of an analogy to the way things like DALL-E work, where you give it a prompt such as I want an image of a dog or a cat or whatever, and that conditions this reverse stochastic differential equation such that it transforms your random noise into a dog or a cat. In this case, what we do is condition it on simulated data with the idea of being able to try to reconstruct and sample from the distribution of true lensing reconstructions. And an example here is shown how this process works in this video. Sorry, it's a little jerky. As we go from white noise, slowly removing noise as we move back along that stochastic differential equation until we end up with multiple samples of the resulting lensing potential. The noise in these maps is significantly lower than that obtained with the quadratic estimator. We also obtain a family of solutions for this. Each one draws from the posterior. This method is incredibly quick and also is able to deal with really complex priors, such as the fact that the underlying field might be non-Gaussian. I think it's quite an exciting avenue for next generation mass map reconstructions. The final component I'd like to talk about is the patchy screening effect. Many of you might be familiar with screening of the CMB. This is one of the key parameters in the lambda CDM model, this tau parameter, which describes how as CMB photons travel from us, they encounter electrons and they scatter some of them off the line of sight and some of them into the line of sight. Patchy screening is a next effect from that, which describes how in regions where there are more free electrons or less free electrons, you get more scattering of the CMB or less scattering of the CMB, depending on that line of sight. And that leads to more or less damping on the CMB. You can kind of see an example here of what the CMB would look like without patchy screening, and an example of what it looks like with some very exaggerated levels of patchy screening. This is quite a small effect. As you can imagine, the size of this effect is larger in regions where the temperature anisotropies are larger. There's sort of more of the CMB anisotropy to damp. And this means that this coupling it generates is a specific non-Gaussian coupling. Despite the fact that the CMB these patchy screening anisotropies have a black body, this non-Gaussianity means we can separate it in a similar way to how we were thinking about CMB lensing. Patchy screening, I think, is a really exciting upcoming probe, as it's able to give insights into two different regions of the universe. The first region is during reionization, when there are large fluctuations in the ionization fraction as the universe transitions from neutral to ionized. And also in the late-time universe, in this case, everything is pretty much ionized, but you have large fluctuations in mass and in distributions of free electrons around collapsed objects. I'm going to present results for the latter region, but I'm excited to think about and work on this reionization epoch with the next generation of telescopes. So this effect is really, really small. So what we do is we reconstruct this patchy screening signal, and then we cross-correlate it or stack it on the locations where we know there to be excess numbers of electrons. In this case, we use the unwise catalog of galaxies, which is a catalog of galaxies from the WISE satellite that covers the full sky. There's a very high source density, which is a nice property we want here. What you can see in this blue excess here is the 2D distribution of integrated electrons along the line of sight on average around these objects. And this is the first detection of this effect, the patchy screening effect. So what can we do with this? Well, we can make a 1D profile by averaging this signal in angular bins. And that's what I'm showing here is these blue data points of that bin signal. And you notice that the signal has a characteristic sort of ringing shape, and that actually comes about for a technical reason due to the way that we've sort of filtered our data. But the thing to compare this to is comparing our data to these different colored lines here, which is when we have gone into a suite of different simulations, the illustrious TNG, the illustrious and SIMBA simulations, identified halos of approximately the same mass, and computed what their electron profile looks like, and plotted that here. This comparison at the moment is quite approximate, as it's quite hard to reproduce the selection function used to select unwise galaxies. But the idea here is to demonstrate what the power of these measurements can tell us about how electrons are distributed around these objects. You can see that with a better knowledge of how these galaxies occupy dark matter halos, we'd be able to differentiate between many of these different types of models. For comparison, we also show what the signal would look like is if the electrons followed the dark matter on an NFW profile, and you can see that would be strongly ruled out by these types of measurements. And so in this talk, I presented quite a few different measurement approaches, and I view these as sort of pieces of a puzzle that we're starting to put together and will continue to do with increasing precision with the next generation of telescopes. So I just discussed how we could get the mass distribution of these objects, measurements of the pressure, of the temperature, and the electron density around these objects. There are other probes such as the kinetic SC and cross correlations, which I haven't had time to talk about. And together, as our measurements improve and we obtain increased accuracy, we're going to be able to make really informative, really high power inferences on the physics governing these objects and how it evolves across mass and across redshift. In the last part of the talk, I want to very slightly change gears, and I will talk about something a little different that connects to probing symmetries of the universe with CMB secondary anisotropies, and I'll show how this links back to the rest of the talk at the very end, so please bear with me a little. The symmetry I'm thinking about here is parity symmetry, and so in cosmology we don't often think about parity violation occurring on cosmic scales, and that's because the physics that governs the very largest scales in our universe, such as gravity, does not violate parity. However, we know that within the standard model of particle physics, there are some forces that violate parity, such as the weak force violates parity. And recently, there have been several different measurements that have potentially shown, although it's not yet established, that there might be hints of a parity violation at play in cosmology. And this is sort of from the CMB side. This is measurements of cosmic birefringence, which is a specific polarization signal seen in the Planck data. And in large-scale structure, this arises in this complex form of a parity-violating four-point function describing correlations between the positions of four different galaxies. And so we started thinking about what other ways could you have of probing the symmetries of the early universe and testing for parity violation. And I'd like to introduce where we ended up by the sense of this sort of cosmic analogy. So many of you probably remember the way that the parity violation in the weak force was detected was by an experiment led by Professor Wu and her collaborators. What they did here is that they aligned radioactive elements in an external magnetic field, so all of them pointed up, and they looked at the direction with which the decay products moved away from the line of spin. There's an interesting thing here is if you consider about what happens in a parity inverted universe. In a parity inverted universe, the spin would remain pointing up, but the momentum would point in a different direction. And this meant that you could use correlations between, this meant that if the underlying physics preserves parity, there should be no correlation between the spin direction and the momentum direction of the decay products. And in fact, what they observed was a non-zero correlation. We can try to imagine doing this at sort of a cosmological analogy. And the idea we have here is thinking about rotating objects. So this could be galaxies in terms of observations, but in the sort of theoretical models we've been considering, these are dark matter halos. And what we looked at was correlations between the spin directions of these dark matter halos and their velocity directions through space. And to do this, we ran a suite of cosmological simulations that included some elements of parity violating physics. And so what I'm showing here, sorry, this video isn't quite working as well over Zoom, is two simulations with identical initial conditions, where in the top case, we have a universe like a lambda CDM universe, and in the bottom case, a universe where we've added a large amount of this parity violating physics in the early universe. This simulation is part of a large suite of cosmological simulations we call the Quixote PNG simulations, where we've been investigating the impacts of various different types of primordial physics on late-time observations by adding them into the initial conditions and running large numbers of simulations of them. The idea of releasing these to the community, they're publicly available on the Quixote PNG website for people to download and use as a testbed for developing new methods of searching for different types of primordial non-Gaussianity. In this case, the type I'm going to focus on is this parity violating physics. So going back to our simple statistic, these correlations between the direction of the spin and the direction of the velocity, we can measure this in a simulation that doesn't contain parity violating physics, one with simple Gaussian initial conditions like lambda CDM, and measure this quantity for halos, dark matter halos of different mass, and that's what's shown here. As you can see, in this case, this measurement is consistent with 0, which shows that in the absence of parity violating physics in the early universe, you don't expect correlations here. What happens when we add in different types of parity violating physics in the early universe? These two models here have different signs of the parity violating physics in the initial conditions. We see a strong detection of these types of correlations between the spin direction and velocity, indicating that this statistic is a very powerful probe of searching for parity violation in the late-time universe. It has also a nice feature that this is quite a generic probe. Typically, searches for primordial non-Gaussianity in the late-time universe are targeted to one specific model. In the case of a 4-point function, one specific shape of correlations between the tetrapod of the 4 galaxies. Whereas this is sort of a more model agnostic. It's less optimal, but can search for a wider range of models. So I said I'd link this back to the CMB, and the way we do this is using the kinetic Sunyaev-Zotovich effect. This is one of the most powerful ways we have of measuring three-dimensional distributions of velocity. The idea here is this effect occurs when you have a CMB photon coming in. It interacts with a set of ionized electrons that have a bulk motion, such as the example here. They're moving towards or away from the CMB photon. The CMB photon will be Doppler scattered by this bulk motion. This means that it generates CMB anisotropies with a black body spectrum that depend on the amount of electrons along that line of sight, as well as the line of sight velocity. And this is a very powerful upcoming probe that people in ACT are using to make precision maps of the 3D velocity field. Get the third component to a correlated effect that I can discuss afterwards. And so this links back to the program that I've been talking about as when we're pursuing ever increasing precision measurements of the primary CMB, we obtain increasing precision measurements of the KSE effect, which we can use going forward to potentially search for violations of parity in the early universe. With that, I'd like to conclude by highlighting that many of the data products that we've been developing, including ancillary products required to interpret them, such as beams and simulations, are all publicly available or going to be soon. In the case of the CMB lensing mass map, this is available now to download, and our Compton Y map will be available in the coming weeks. I haven't at all talked about in this talk, of course, one of the primary goals of these CMB experiments is to make precision measurements of the black body components, so the temperature perturbations and the E modes and also the B modes. This is an exciting thing that we're working on in the collaboration and continuing to reduce. And hopefully you can stay tuned for some updates, hopefully later this year, with our new cosmological inference from these measurements. Thank you very much for your time.